All right, so we got problem 6.26. It says the two parallel inductors are connected across the terminals of the black box at time equals 0. The resulting voltage V for time greater than 0 is known to be 12e to the negative t volts. It is also known that I1 0 at time 0 seconds is equal to 2 amps, and I2 times 0 is equal to 4 amps. So it means that at, at 0 seconds, these inductors here are going to hold current. And yeah, so then it's for the first question, it's asking us, I'm going to label these as A, B, C, D, E, F, G. Okay. So for A, we can just say L equivalent is going to be equal to 3 in parallel with 6. And off the top of my head, I don't really know how to do that, but 6 is 2. Okay. It's going to be 2 Henry. Let me write that. Okay. And now it's asking us to find the current for time equal or greater than 0. So we know that our V is going to be 12 e to the negative t. And yeah, so our V would be the voltage across the black box, right? So we use Ohm's law for this. So we know that our equation for V, well, we know that the voltage across an inductor depends on the inductance times the I T dt, correct? So we play with this. V dt equals 1 over L di. Okay, so then we can play with this. Oh, as well. So T is going to be equal to, so the inductance is 1 over 2 times V, and this is 12e to the negative t dt. So we get 6. Here. And oh, I forgot to account for, so in here, so here at time equals 0, so we know in this node we have 2 amps running this way, so we know our IT is going to have IT at 0 is going to have 6 amps. Regardless. So we have to account for these 6 amps. Right? And so now we just do the calculus. So 6 to the negative t minus e to the negative 0 plus 6. Right? 6 e to the t minus, e to the negative 0 is going to be 1. So negative 6 plus 6. So our function for a current would be such here. All right. So to find I1t for t equals greater or equal than 0, I'm gonna move this down here. Okay. All right. So now it's asking, okay, find I1t for not at t greater or equal than 0, right? So we know we can do this equation again, like the above. We have the equation for the inductor. V equals L E I T dt. Equals V over L, right? And you have to account for the current times 0 from the inductor. 0. Okay, so we have it's 12, yeah. So inductance across is 3. So it would be 4 t 0 e to the negative t plus 2 I t equals 4 to negative t minus e to the negative 0 plus 2. Wait, yeah. Yeah, so it's this. Two. Let me just revise this and see if this I'm on the correct track. So I1 is 2 milliamps. We have to account for that. So, okay. Mm. Okay, seems to be right. Now I'm gonna do it for I2. Oops. So I2 T4 T greater than 0. Same equation, V equals L D I T over dt. Plus 4. All right. Okay. Yeah. So then continue the same thing. All right. So now we want to calculate the energy delivered to the black box. So to calculate the energy, we first need to calculate the power, and then you want to calculate and to calculate the our first step would be to calculate the power, and then our second step would be to calculate the work, which work is it would be the integral of the power. Okay, so for our first step, we know our current equation for time greater or equal to 0, right? So current would be 6 or t 6e to the negative t, yeah, and then our voltage is 12. So e to the negative t. All right. So if we multiply these, 6 times 12 is 72, e to the negative 2t. And then for our second step, take the integral of this. So this would result in 72 over 72. It would be negative 36, negative 2, infinity and 0. And then e to negative infinity would be 0 minus negative 36 and 36 joules work. So then continue on to the next one. Right. Okay, so now it's asking how much energy was initially stored in the parallel inductors. So we know the formula for, well, next question. So we know the work of the inductors is going to be 1/2 L times inductance times current squared. So we have, in this case, we have 2. We have the work or the energy, which we calculate across the 3 Henry inductor and then the 6 Henry inductor. So we have this. Oops. So it's going to be 1/2 times 3, and then we know here that the current at I1 equals 0 is going to be 2 amps, and then 6 times 4 amps squared. So here we're going to have 6 joules, and then 48 joules for our 6 Henry inductor. Okay, and yeah, this would 6 joules for the 3 Henry inductor and 48 joules for the 6 Henry inductor. And the total energy between these two would be 54 joules. Okay, so it's asking now how much energy is trapped in the ideal inductors. Just maybe go here. Okay, so okay. So how much energy is trapped in the ideal inductors, right? So, okay. So how much energy is trapped in the ideal inductor? So I'm assuming our ideal inductor, he means the equivalent. So yeah, so 2 and then I1 at 0. I guess we can do this instead. We can do 1/2 1/2, we have 2, and then the current across I1 is 2 plus right. So actually, we can think about this as already, so as energy trapped in the ideal inductors, we think of this as Yeah. So it's two, yeah. Um, we can think of this as uh, the total energy stored, which is 54 joules, minus um, the energy being delivered, 36 joules. Um, yeah. So how much energy was this just starting from? Yeah. So that would be 18 joules.